Sweet. That's loud in here. Well, welcome everyone. A lot of times I think I would prefer to, let some stragglers come in and whatnot. But since we are going on YouTube, we'll go ahead and just get started and people can walk in and sit in the front and be embarrassed, right? So, for those of you that don't know me, there's a few people I don't know in here. I'm Aaron Kopp. I'm been tasked with training and recruiting here at Pulse Sound, so we're going to hopefully be doing these classes a lot here in the future with a lot of different topics. This one always seems to be a popular one. So, real quick, do we have, Tyler, do you have the remote for this? No, the TV. Well, no, I can hear the audio through it. Yeah. And as a sound guy, it's going to drive me nuts. Okay. Anyway, we'll work through that. Just so you guys have a little bit of background on me, I've been working in the audio industry for, 26 years now. So I got to start when I was young, and I've been teaching classes I've taught classes at BYU, UVU, all in live sound reinforcement. So that's just the quick background on me. And I do like a lot of interaction from you guys, so please do not feel scared to raise your hand, ask questions, make comments. Even if it's at my expense, I don't mind. I don't mind a little heckling from most of you. But, and one of my big philosophies in life is I don't expect to know everything. What I do expect is that all of us as a whole will know everything. And there's a lot of things, I'm just going to be straight up with you guys. There is, I don't pretend to teach the exact right principles all the time. Sometimes there's concepts I want to teach that get an idea through that aren't going to be 100% technically right, and I'm okay with that, personally. So as long as you guys understand a concept. So, however, if I do something like that, and some of you are like, well, I was taught something a little different, and you want to raise your hand and be like, well, I learned it this way, I'm okay with that. We can acknowledge that, and then we can discuss it deeper for those that want to go a little bit deeper. So, I'm not the end-all be-all, is what I'm really trying to say. I'll let you guys, if you guys don't know everybody else in the room, there are some guys in here that are definitely much smarter than I am. And I know those guys will also not be afraid to call me out. So, I'm okay with that. With that, we'll just kind of get started here. I try to keep things not so boring, so let's not be so boring about it. Let's just have a good time. This is one of my favorite statements that I ironically came up with myself, because it's the way I like to live around wireless. So I've walked into many scenarios in my career where I've seen wireless mics set up, and I look at it, and I'm like, that's a huge mistake. And yet, somehow, the show didn't have any issues. However, all of a sudden, I've walked into other scenarios where it's mistake after mistake after mistake, and they have huge issues. So I honestly believe that a lot of times you can get away with mistakes or maybe some compromises, and you might be okay. And if you understand what you're doing, you might be willing to take that risk. But it's the mistakes after mistake after mistake that really causes the wireless failure. So just a quick little background on how we determine wavelengths of radio frequencies for wireless mics. So when we talk about megahertz and frequency and wavelengths and all that, this is the equation we're looking at and what's being calculated. Personally, I don't think it's really important to memorize any of this. That's what we have Google for. What the important part is that you just know the parameters that you need to type in to get the answers that you need. So, all right, here's just kind of a basic little chart of radio waves and kind of what each section is all about. So when we're down to 30 hertz, you know, and what is considered the very low frequencies, and then up to the low frequencies, medium frequencies, radio waves, microwaves, infrared, then visible light, X-rays and gamma rays. So what we're looking at is for a majority of wireless mics, we are going to be in this UHF, or ultra high frequency, in the 470 megahertz to, depending on your licenses, up into the 600s. It used to be a little bit higher than that, and we'll discuss that later. So, yeah, it's just kind of a quick rundown for you. All right, so what we need to understand about waves traveling, and I'm going to assume that we've got anybody here that's fairly new to the industry up to a lot of seasoned pros. But what we need to understand is as waves travel and interact with one another, and this is relevant to acoustic waves as well as radio frequencies, how they interact with themselves as they bounce around in a room or in free space. So really what happens if you have a wave and it interacts with itself over there on the left, and they are in phase, so basically going up together, down together, they will actually double in strength. So you get, on the left, you get the wave over there, and then the resulting is that. Now, if you get them slightly, that's the same thing, but I just noticed that. That's great. See, I make mistakes all the time. So, what is cool about this animation is you can watch the waves interact. So you got your yellow wave and then the gray wave behind it. And as you see, as they come into phase with one another, the purple wave is the resulting wave. So when you get two waves that are actually out of phase or just exactly opposite out of one another, they will completely cancel out, essentially just disappear. And that's really detrimental. And once again, this happens with audio waves as well as radio frequency waves. So what happens if they cancel all the way out? That would be what is a classic dropout for your wireless mic, because there's no signal getting to your antenna. Now, this can be, we're going to view what this can happen in a room. So if you've got your radio frequencies bouncing around in a room and they come together, all the parameters are right, it creates what's called a standing wave. And to visually see this is actually pretty cool. So we're actually going to watch this. So this is just water in a pool with a single source in the corner, and you start to energize the water, and it looks pretty whatever at first. Then as you watch it develop, you're going to see what's called a standing wave develop. So now we're in complete standing wave. So basically what's happening is right in the same spot, you're going from a low pressure to a high pressure. So if this is happening in your room, in the standing wave, and you happen to put an antenna right in that, in the standing wave, whether it's getting high pressure or low pressure, you could get a lot more signal, or you could potentially just get zero signal. So that is actually happening in the room, whether you see it or not.
So, sorry.
Yeah.
So you're saying when you get, when the waves are out of phase, like the pool was rippling, you come to a point where the pool's completely still again?
Uh-huh. Yeah. There's a part where it's right in the middle, and that's where it's going to be basically just still, as if...
Nothing in that pool.
Right. Well, not in the whole pool, but in spots of the pool. Right, okay. Sweet. So we're going to go, huh? We're just going to talk about how waves travel around objects. So if you are unaware, radio waves and metal don't get along. So as we look at this, what we're looking at here is the wavelength being the blue lines, and then we have a metal obstacle. You can see that the wavelength here is actually larger than the metal obstacle, which means it's going to flow around it. So it's really not a big deal. If you want to actually kind of see this animated, this is kind of what it's going to look like. So right up there would be your metal object. The wavelength is much larger than the metal object. It just kind of works its way around it. So, and once again, we're talking about waves, so this is relevant for acoustic waves as well as RF. Now, the problem is, if our wavelength is shorter than our metal obstacle, it's going to block it. Maybe not block it completely, but it's definitely going to create a shadow, and looking at that animated is more like this. So you can see right up here, there's a lot of shadow, and it's pretty weak all through here because it's not making it around.
But there's still something going through.
There's a little bit of going through, but that's dangerous territory. So it's going to be really weak.
It's going through, but also look how messy and distorted it is on the backside too.
Yep. So I mean, that's a single source up there, so you've got some nice rings here. As it comes around, it's almost like it's got two sources and creating more phase issues. So I'm pretty big on visuals, at least I think I am sometimes. So when I teach, people that I know are definitely new to the industry. It's like I've got this little net here. And if the net were metal, and that's my, let's just say it's like a chain link fence, I've got the holes there. But if my wavelength is this big and I put it through the net, it gets bounced back to me. But if you take something smaller than the hole of the net, it goes through. So, I mean, that's really almost as basic of a visual as I can give you. So, the fun thing with this now is, well, we're going to go on just a little bit farther. So it's the same like I just demonstrated with the net right here. If my wavelength is smaller than the opening of my metal object, it'll actually make it through. If the wavelength is larger than the opening of the metal, then it's going to get blocked. So I've heard of this example several times. All these cities, you know, build new baseball diamonds every year. And they, especially if you've got 4 baseball diamonds, you know, and there's the central little hut where they put the controls and everything like that, and that's where all the 8, you know, wireless mics or whatever are. And then at the beginning of the baseball season, someone goes out and, you know, big opening of the park and they want to sing the national anthem. They send them out, you know, out to the field to sing the national anthem. And they've tested the wireless mic previously, everything's fine. They send someone out there for the first time. They didn't test the mic out in the field, and all of a sudden it doesn't work. So what's in between the pitcher's mound and the hut in the middle? What's that? The fence. It's kind of an issue, especially if it's a tighter fence, you know? It's going to block a lot of that RF. So, you know, there's things to think about when you're looking at potentially planning out wireless for events or whatever. What's in the walls? Are they metal studs? Are they wood studs? Is there rebar in it? There's a lot to consider if you're trying to, you know, which actually metal studs or rebar in a wall could very well be to your benefit if you're trying to isolate a bunch of wireless mics in a venue. It'll help you a lot.
Let's say if you're in a confined space, does that matter?
Yeah.
In just a room, the studs matter?
Absolutely. Yeah, now where it can bite you is, remember, if it can't get through, it's going to get reflected. Which, now let's go back to the pool when we're creating standing waves. So You got to keep that in mind too, which brings us to, let's see what it looks like with transmitting RF in free space. So right here we'll have, this is our transmitter. I know it looks like a speaker, pretend it's a wireless mic. So this is just a perfect world, nothing interacting, it's just going through air. You can see that all these spots right here, if we were to place an antenna, they all get roughly, the same strength. So we can see that there's nothing bad going on here. This is a perfect world. How many of you live in a perfect world? Yeah. Okay, so now let's take a look at really what's might be happening. So we're just going to add a little metal obstacle up here. So you have your transmitter, it bounces off the metal, and we start getting reflections. And now we can see where we place our antenna is actually a big deal. So especially if you were to choose the location of this guy, which is almost a complete dropout because of the strength that it's getting right there. So another thing to keep in mind here is antenna placement in a room is crucial. And let's just say you're having a lot of issues with your antenna being right here and you're not getting very good strength. You might just have to move it 1.5 feet, and all of a sudden you've got a new location in the room where you're actually getting a reflection and you're getting phase summation. So you're actually going to get maybe a slightly stronger signal off your wireless mic. So pay attention to the strength of, that you're receiving on your receiver so that you can make adjustments to your antennas. Yes?
What's a SRDS USSL? Right there.
That guy? Stage right, stage left, down stage, up stage. Yep. Really not. Yeah. It's all good. All right. So now one of the things that we can do instead of a single antenna placement, it's been obviously around longer than, well, I remember using a wireless mic with a single antenna. I don't know if any of you remember using a wireless mic with a single antenna. Anybody here beside me remember using a wireless mic with a single antenna? You? So you're as old as I am? Because, yeah, that makes me old. So what using the two antennas will do for you, and there's different kind of ways to do this. Lectrosonics does it different than Shure a little bit. But the advantage is I can now place two antennas in the room, and because we know that once again, a perfect world is this transmitter never moves. So I can place my antennas where I get the best strength on both, and I leave them there, right? Well, the problem is, even I'm doing it, wearing this wireless mic pack, am I staying still? No, which means this phase cancellation is constantly changing in the room and the location of where you're getting good strength and bad strength. So the idea between the two antennas is that the receiver is going to choose which antenna is getting the better signal, and it's going to go with that antenna. And that is the whole concept behind diversity. This is one of my favorites right here. That's dangerous territory. Okay, so now that we've gone along with how the waves are kind of propagating and stuff like that, we also need to know other things that are happening within the wireless mic. The way we hear, there's a lot of bandwidth, and really to transmit that is just a little bit cumbersome. So to make it more efficient, what we need to do with the audio that goes into a wireless mic is we've got to compress it. We've got to get it down to something that's more easy to transmit. So wireless mics are doing this. They'll go through a compression process, so it can be easier to transmit. And then on the receiver, it's going to get re-expanded. And so this is just kind of showing what that ratio is. Once again, for this kind of surface level training that we're doing today, it's not really important for you to be like, do the math and figure it all out. it's more that you guys need to be aware that this is happening. And the reason I like you guys to know that this is happening is for a couple of really good reasons. One is we're all audio guys. So what happens if you take, you go into the studio and you make this beautiful mix, and then what do we do to things these days to make it go on Spotify with the original file? What do we do with it? We compress the crap out of it. Okay? So we compress it. What does that do to how it sounds? It sucks. It depends on the algorithm. Okay. Now, so what happens if we do like, I'm going to take this beautiful WAV file, I'm going to go down to MP3, and then I'm going to expand it back out to WAV. Is that a perfect conversion? No, we're losing stuff, right? So that's the thing that's happening here as well, is through this whole process, you're going to lose a little bit of audio quality. Now, have any of you actually ever heard this degradation in audio quality? A couple guys? Yeah. So
only one time in a controlled scenario.
there you go. One time in a controlled scenario. So if it's just a couple of you guys that have heard this during a show, to the general public, are they really hearing this? Do they know what they're listening to? Not really. Not even the guy that probably comes up to you after the show and says, hey, I'm an audiophile. Yes? No? Am I the only one that gets those guys?
Oh, no.
Okay. I didn't think so. All right.
Dan Morgan recently yelled at a band for this exact thing. We had Accent Digital on the show, and the band guy was saying that he could hear the compression happening in his microphone.
Yeah.
That's the only time Dan Morgan curses somebody.
Psychoacoustics is a wonderful thing. Anyway, so this stuff is definitely happening. All right, so now that it's gone through this process, let's kind of discuss how the next process. So I like to demonstrate it like this. Once again, I know this isn't exactly how this is happening, but it gets the concept through. Okay, so when you flip on your transmitter and there's not a microphone attached to it, on a spectrum analyzer, it looks like that. That's your frequency. It transmits. As soon as you connect your microphone to it, and I should throw out the disclaimer that this is analog style, it starts modulating back and forth. And this is called frequency modulation. There's different ways to do it. Most analog, I'm not going to say all because then somebody brings something up, but most analog microphones, it's basically like a speaker moving back and forth. There's a device within the microphone that's taking that audio signal and matching it to a frequency so it moves back and forth kind of like a speaker so that it can be transmitted. And then when it gets to the receiver, there's another device that takes that radio frequency, demodulate or converts it again into an audio signal. That's where I'm trying to go with that. So this is the concept that's happening. There's other ways to do it. You can do it, Radcom for their comm systems actually uses what's called amplitude modulation, which means it actually takes the strength of the signal and fluctuates it this way instead of this way. But once again, the concept is the same. You've got to match an audio wave. All right. So now what we're going to discuss is kind of how the spectrum is split up and how we're going to kind of allocate things and how wireless mics are going to live in this shared space in the world. So once again, most of you were probably born about the time that analog was switching over to digital. Oh my gosh. Anyway, so originally television stations were analog, and what the FCC decided to do was a TV station, when you hear that term, a TV station represents 6 megahertz of spectrum in space. And the reason they did that is so that the TV station would, on a very strong signal, transmit a video, an audio signal, and then color. So the TV station had to operate within that 6 megahertz. So arbitrary numbers, TV station around here, let's say Fox 13 would operate from like 440 or 470 megahertz to 476 megahertz. That's a TV station. So, and you get allocated your space from the FCC. So back in the day, some of us that were brave or desperate at the time, if we got into a situation where there's just a crowded space or our microphone didn't fluctuate where we could put it, some of us would get brave and actually park a wireless mic in here. Legal? Not so much. But if you were desperate and knew what you were doing, you could get away with it. Well, then, you know, the FCC said, well, all the TVs need to go digital. Well, what happens when you make the jump to digital is instead of getting the space down here, in order to go digital, the TV stations have to take up the whole entire chunk of spectrum. So if you get desperate, there's no more cheating and trying to do something that you shouldn't do and park a wireless mic, because you do that here and you're just going to get destroyed. So here's a scan of actually what it kind of looked like as people were making the transition. So you have a mixture of analog as compared to digital TV stations. So unlike the previous slide, you can see that the digital isn't quite, you know, as flat as you want it to be, but it's the concept that we're after here. So wireless mics started going down the same path, and we'll get to why digital takes up the entire chunk here in just a moment. So there's a couple of different ways to transmit audio digitally over RF. And the first way they kind of did it was, hey, if the frequency touches that side of its modulation, it would represent, for example, a 1. If it came to this side, it would represent a 0. So you get two numbers there. Well, to do that fast enough and actually make a really good audio signal, it wasn't fast enough, it wasn't efficient, so it didn't sound that great. We're talking like low quality MP3 at first. So it took a little while for, you know, people to perfect what they wanted to do to transmit analog audio, and we ended up with something that looks more like this now, which is called 8 PSK, or 8 phase shift keying. So what happens is along this mesa up here, as you go along, there's different points that represent different combinations of 1s and 0s for digital. So it might be, in some spots, it might be 001, 111, 010, whatever. And what it kind of looks like on a graph is a little something like this. Once again, this isn't super important. This is kind of just for people like me, really fun to look at, to figure out how people are actually doing this. So what happens is as you shift your phase and amplitude, then you can start getting all these different combinations of 1s and 0s, and the more efficient it becomes, the better quality digital signal you can get. So as you're doing all of this, that's what creates the mesa across the top. And this one right here, the 16, that's super cool. Is anyone doing that yet?
Can I tell you something really cool? Sennheiser.
Is Sennheiser?
9000 series. This is 64 quam.
64 quam?
64 dots in that grid. 64 possible locations that their
Yeah.
signal could be. The Sennheiser 9000 is the cleanest audio out there right now.
So Sennheiser's doing it. But yeah, this is, I mean, to me, that's some genius work right there. So just another kind of demonstration of, you know, I know this one right here doesn't really match up with stuff, but it just kind of gets you some more information, like on a wave, if it's 0 degrees, it represents 3 zeros. If it's 45 degrees, 0, 0, 1. So just kind of some fun graphics to kind of let you know what's happening, what it kind of looks like, and how it's allocating all of its ones and zeros. Once again, we're going to go back to kind of putting compression and ones and zeros back together again. As we do it digitally, if you're not aware, people have codecs. So codec just being code decode, which MP3 is a codec, AAC, wave, they're all codecs. Back in the analog days, it was a lot easier if you had a really cool scanner and it was an analog signal. You could tune your scanner into that wireless mic and you could listen to it. Well, now with all the digital thing and all the manufacturers having their own proprietary codecs, you can't do it with just any scanner. You have to have the correct codec in order to figure out or listen to the audio that's being transmitted. So yeah, just some more general information. And of course, the goal is to get your highest quality codec so that your audio is always the cleanest and best quality. And also remember that as you're running through all these codecs and all the digital stuff, that you're adding latency to your audio signal, which, in your whole audio path, every single little bit of latency you put on it just makes it more difficult to deal with as a performer if you're hearing it out of a monitor wedge or something like that, or your in-ear monitors. So once again, everything these days is getting so fast and so much better than it used to be that it's really becoming not a huge issue. The other thing that's helping with codecs and latency is everybody growing up right now, performers, that's what they're growing up on. So you're used to hearing the delay and latency. And because that's what you grew up with, you think it's normal. So a lot of the guys that were coming off of wired microphones and monitor wedges with analog that was very low latency, when we started making all this digital transition and there's longer latency times, there were truly some musicians that could hear the latency between their mic and their monitor wedge, and it would drive them nuts. So once again, if that's what you grew up with, you're going to hear it. If you grew up hearing latency, you just assume it's normal. So once again, it's becoming less and less of a deal. All right, so now let's talk about our world and our environment, how we're existing in this world with TV channels and everything like that. Once going back to kind of the very beginning of class and that diagram we looked at and the allocation. So these are all the different bands that, RF we kind of use on a daily basis, and what the attributes are of each band. So, 30 to 45 megahertz, very long antenna length, RF distortions, high noise floor. Back when I was growing up and TV stations were in VHF, that was cool. Long antenna lengths, good wave propagation. What do we mean by good wave yeah. So there's in the environment, or this is your noise floor. So nothing's transmitting, but this is what exists just in the room all the time. And down lower, this noise floor would be a little bit higher up. So yeah, which means you've got to have a higher strength to overcome it. So, yeah, VHF. So what does good wave propagation mean? You're getting out. Well, let's expand on that a little bit more. What does getting out mean? Doesn't get us blocked as easily. They go far. Go far good. Yeah. So VHF right here, it's, you know, once again, we've got some good wave propagation, but, you know, So 450 to 698. This is what we call the beachfront property. Everybody wants to be there because the frequency range is pretty wide. You've got great wave propagation and your antenna lengths are actually manageable. So everyone wants to be here. And when I mean everyone, I mean everyone. Verizon wants to be there. T-Mobile wants to be there. Google wants to be there. Microsoft wants to be there. Audio World wants to be there. Yeah, ham radio people want to be there. Yeah, because it really is like the sweetest of all the scenarios. So there are some like wireless mics that might be up in this here area. You've got decent wave propagation, not a whole lot of bandwidth. Here's the big one. Be aware, there are wireless mics in the 900 megahertz spectrum. It is unlicensed. It is a free-for-all. It is martial law. So good luck. It might work for 5 minutes. It might not work for 10. Yeah.
We have some ULXD in X52. QLXD in X52.
Yep.
Which is 900 megahertz. And there are certain venues we just cannot use them in because the noise floor or other devices is too strong.
Yeah. For all my lighting friends out there, a lot of their wireless DMX is in the 900 megahertz.
Also, Greg just found on a show, he was just on RFID readers at conventions, 900 megahertz.
Oh, awesome. Pyro, 900 megahertz. that could make the day interesting. So, just kind of go through this and, you know, fine. This is just kind of general info of what's happening. There are some wireless comms in the 1900 megahertz. It says business equipment, typically high latency. 2.4, we all know about 2.4 and why it's not great because everything's Wi-Fi and hard to deal with. All right. Any questions to this point? All right. So,
I said, don't change that just yet, please. You go, okay.
huh?
It's okay.
Audio guy.
Yeah.
Do you want that?
Just for
I can give you this slide. That's all good. All right. So, once again, some decent amount of years ago, let's say 2009, to some people that I talked to, including my kids, that was like, you know, dinosaur age ago. This is kind of what the spectrum was allocated as. Once again, these are, on this side, these are TV channels. And from VHF up here, and then 470 all the way up to 800. And depending on your area, even, you know, the cities and stuff, TV channels were spread out throughout this whole spectrum. And it was pretty easy to find open channels for wireless mics and for everybody to coexist, and it wasn't too bad. Well, then the government, in their brilliancy, discovered that, hey, there's some companies that really want to own some of this really cool spectrum, and they're willing to pay a lot for it. So they decided to have an auction, and they did some research, and of course, the way the government researches, they said there was like some absurd number, like only, what, like 1,000 wireless mics in use in the US at one time, because audio guys would never register for licenses, even though you're technically supposed to. So they're like, we're not going to affect wireless mics users that much. There's not much going on, and we can get millions upon millions for this airspace. So they auctioned off a chunk, and it was very, very lucrative. And so they were like, man. Well, after they auctioned it off and all the people freaked out in professional audio and entertainment and broadcast, they're like, well, that's too bad for you guys. But we made so much money, we're going to do another auction, and sold off another huge chunk. So now what we're dealing with is that is all now gone. Now, also keep in mind that all of this space was open for wireless mic and broadcast, but it was also where TV stations were stationed, or that was redundant. And so all the TV stations that were there, they had to go somewhere. So now it's like, hey, all this spectrum over here, all of these TV stations had to start to go occupy as well. And now we're really in a crisis mode, per se. So now we have to try to get our wireless mics like in a chunk here, and actually this amount of TV stations is actually not too bad. Places like LA, Chicago, New York, Dallas, Phoenix is more crowded than this. So now we have to start working a lot harder at our jobs, which really, really kind of sucks. So to kind of give you guys an idea of what happened just here in the Salt Lake area, my good friend Chris Dye took this scan up at two separate scans up at the University of Utah. The green one would be pre-last auction, so it looks pretty good. And then all these TV channels had to move, and the red would be the result after the auction and after everybody had to move. So you might say, well, that's open. Well, nope, that was auctioned off. So really, you're trying to put your wireless mics in from there to there, when previously it was pretty wide open. So, and this was years ago. It might be more crowded than that in the Salt Lake area now. I can't remember. Chris will tell us in a moment. Okay. It's more crowded.
Yeah. There's a few more things around like 14, 15, 16.
So right in here? Yeah. Maybe some low power stations. So that's currently what we're dealing with in our area. All right. We're going to talk a little bit. Sometimes it's hard to kind of keep RF mics in a nice linear way of how we're talking about it, but we're going to talk about how RF actually propagates through space. So what we've got here is RF actually has two waves that have to coexist together. There's an electric field and a magnetic field. So what's happening is, as this goes along, your electric field is going up, down. Your magnetic field is going left or right. Direction of channel, or direction of travel. So there's the two actually phase things that we need to be aware of with wireless mics. Now, what that really looks like as it's moving is going to look a little bit more like this. Moving along. So you can see as they kind of go along, what's kind of happening there. And the green arrow is the resulting wave of how it actually exists in air as it moves along. So this is when the two fields are together. Once again, the amplitudes may differ, but the waves must be in phase. Okay? Now what happens if we shift one out of phase just a little bit by, let's say, a quarter? So they start moving along like this. What happens is the resulting wave actually becomes not linear back and forth, but it starts to get more circularly polarized. So this is going to be important to remember here as we start talking about antennas and propagation. But I just thought this was kind of a cool animation to kind of show what the resulting wave was all about. So antennas all have a radiation pattern. Which means how the energy is coming off of the antenna itself. So there's tons of different kinds of antennas. And you can actually see up here a quarter wave, just straight up and down, how it's going to radiate off the ground plane. Half wave dipole, how it radiates. This is more of a, a dipole over here. And then a Yagi gets more elliptical, which means you're going to get more forward energy out the front of it. So once again, because we're just talking about waves and waves and waves, think about it as your microphone. Your microphone has a pickup pattern. So you talk into it at different places around the microphone. It's going to sound different. It's going to pick up different frequencies, better or worse. It's the same with antennas and their pickup pattern. So at certain points around how the antenna is made and how it picks up, it's going to get a stronger signal, weaker signal, and could really affect the reception strength of your microphone. So, and really, antennas are just pieces of metal. There's really not a whole lot of specialty things behind them. So let's talk about different antenna types. So I don't have all of these here, but we'll talk about it. That right there is a quarter wave antenna. How do we know that's a quarter wave? It's short. Yeah, okay. What frequency, Chris? So yeah, but that's actually a good question. What frequency is that a quarter wave at? The quick way is actually just read the documentation that came with it, So you could go back to the beginning of class and maybe get a little ruler out, measure that out, and you can do the calculations and you can find out what the quarter wave frequency of that would be. So quarter waves are typically really short, stubby. Do they work? Of course. These are not the most efficient at getting signal. So they work, but yeah, not always the best. I'm conflicted with this one. Because I could say this is a half wave, right? And you're like, because it's longer, right? Well, this particular antenna is a little deceiving. Because if this is quarter wave and this is half wave, then it should be double, right? So, but why is this longer than double? Because this is really actually, it is half wave, but what's hidden in it is this is actually a dipole. And you have to know that because there are half waves out there that do look exactly like this, but they're for a longer frequency. So what's happening in here is there's actually two parts to this antenna. There's half of the antenna comes this way, and in the middle there's a junction, and half of it's coming this way. So really, it is a half wave. So there's that, and then the other half would be that way. So the cool thing about this one, so this is a dipole as well. It's just a little beefier. The cool thing with with this dipoles is you do not. Oh yes, sorry.
Sorry, the dipole you have, the color stripes on that are. I mean, I've noticed them on our equipment. Are they different because of different frequencies depending on the color?
Yes, and that's per manufacturer. That's per Shure. So Shure, and even down here that'll tell you what frequency it's good for. Okay. So that's just so you can more easily.
Not just a universal, that's per company. Okay.
Yeah. Right. Not everyone does that. And this one right here as well says that it'll most of them will be marked what they're good, what frequency range they're good for. The cool thing about dipoles is you don't need the ground plane. I haven't talked a whole lot about ground planes, but antennas do need a ground plane, like a reference, just like almost anything electrical signal. So what makes this not needing a ground plane is that I can actually remote mount this without a metal plate behind it. Same with this one. And the reason is because dipoles, because half the antenna comes that way and half the antenna goes that way, it's actually creating basically its own ground plane within itself. So that's why these guys are kind of cool. But going back to, there are antennas out there that do look like this, that are half waves, true half waves. I've seen true half waves mounted to a wall without a ground plane. Remember at the beginning I said one mistake? Not knowing what kind of antenna this really is could be that mistake. You remote mount a half wave and it's not going to, and doesn't have that ground plane, your reception is going to be really poor on it. So, yeah. Next up, LPDA, which is this guy. This is in a couple of previous slides. This one has the way, you can come up and take a look at this later, but within here, there's copper that comes down that way, that way, that way, just like that. This one has the holes in it. For what purpose? Nothing more simple than just let the wind blow through. So, because even these, I've seen these, the wind catch these and just take them over. Anybody lose fins to the wind? Yeah, it kind of sucks. So, what's happening here is this is basically an array of dipole antennas. You got your shorter wavelengths here that get picked up down here, and it all combines, the energy all combines eventually down to one connector, but your longer frequencies are here and get picked up better down here. But because of these all interact with one another, it creates forward gain or better reception out the front. So just by the nature of physics. So if you haven't ever really looked at one of these guys, it's worth coming up and looking for, at just the copper strips on this. Once again, manufacturers are very proud of these things, but this is seriously PC board and copper tape with a coating to a connector. You know, they've put some more R&D into it a little bit more, but yeah, antennas aren't really all that complicated.
Is that just a one-way antenna? Just shoot it straight?
Yep, that's it, that way. So its pickup pattern is that way, that way. This one is omnidirectional, so all the way around it. Yeah? Okay. Uh-oh, here we go.
You said antennas are like just pieces of metal, not that complicated.
Yeah. So Chris is, okay, here we go.
That is?
Yeah. This thing that looks like it just came out of a ham radio guy's briefcase, which it just did, is literally just a piece of wire with a connector on it.
About a third of the way up from that junction.
This one?
Yeah, a third of the way down the cable.
Uh-huh.
Other way. You'll find another junction.
Oh, right there.
There's just a little slit in one side of the wires right there.
A little notch right there.
Dipole.
Yep. So, yeah, they're really quite simple. We'll call that a piece of wire antenna. All right.
That is actually technical.
All right, then we get into cool stuff. If you haven't seen one of these, my favorite thing is I can't count how many shows I've been on now where this is set up at the side of the stage and people will come up to me at the end of the show and be like, "What is that?" And I'm pointing at this guy. I'm like, okay, so this whole show with all this thousands and thousands of dollars of equipment, and you're most impressed by this guy. And most of the time I tell them it's a government tracking thing, just for fun, and just to see what the reaction is. But really, this is just, the reason that this antenna is cool is because one, it's circular. So this is its ground plane. And remember the animation, if we take one of those wavelengths and we shift it out just a little bit and the wave becomes circular. So if it's circular and this is circular, then it's going to solve a problem that we're going to talk about in just a little bit with antenna polarization. So this guy, and just because it's circular like this and the way it was designed, there's actually a lot more R&D that went into this, even though, once again, this is a plastic tube, copper metal. I can feel it right there. Just screen, like it looks like it could be my screen door, okay, with a piece of metal in the back and a connector. This one has, because of the way it's arranged, once again, has a lot of forward gain on it. You can either throw and gain a certain amount of strength out the front, or its receive area is more sensitive out the front. So this is really kind of cool. All right. So the rest of them, you can see the IEM radiator. It's just a different design to get forward gain. The spotlight one is kind of cool. You can put it underneath a stage or something if you know a certain presenter is going to be underneath. That way you don't have antennas to the side being obnoxious and, you know, with people being concerned about sight lines all the time. Another couple of examples of dipoles. The one on the end is kind of cool. It's made by Lectrosonics. It's just got 2 set screws, and you can't really see it, but then down the side, it's got frequency lengths. So you loosen the set screws, you adjust the slide of the metal to optimize which frequency it's going to be for, tighten the set screws back down, take them back out, swivel them back out, and you got a dipole antenna that's tunable. I mean, really just really simple things when it comes to antennas. And this one was gotten there twice. So we're just gonna wait for it. So at this point, we're going to just take a quick little 5-minute break. And then when we come back, we're going to discuss why antenna orientation is going to be really important. So go there's some drinks back there. If you need to grab a drink, use the bathroom real quick. Yeah, let's try to be back in 5 minutes. All right. Get everyone back real quick. So let's talk about, just real quick, with these antennas. We talked about different types, maybe some advantages, disadvantages of all of them. So just like with microphones, monitor wedges or noisy environments, with your microphone, you might want a different pickup pattern on your microphone, right? So if this has a specific pickup pattern, then let's say you're on a show with a video wall. And video walls are definitely a big thing now, and I'll show you why a little bit later. But video walls put out a lot of RF, so they take your noise floor way up. So if you want to just take the noise floor from your video wall, then you want to put this with the backside to your video wall so it's rejecting that noise floor so that you get better reception from your wireless mics. So you want this portion of your microphone closer to your transmitters than you do, and then put this towards your noise floor. Yes, Hayden?
Does that matter if it's like the antenna does that be directly in front of the LED wall to make that effect, or can it be like to the side of it but still laterally in front of it?
So he asked, does it matter if the antenna is to the side of the LED wall, or does it need to be directly in front of, position of it? The answer is, basically, if you're in the same plane and this pickup pattern is kind of, let's just say it's somewhat cardioid pattern, it's actually more elliptical, but it still has pickup from the side. So if your noise floor is the video wall here and you're to the side, you're still going to get a decent amount of noise floor. So you want to make sure that your noise floor is to the back of this guy. So if we come back to this guy, where this has got a really nice mesh thing to the back for its ground plane. Once again, if this is to the back side or to the side of your video wall, this is going to help reject a lot of noise floor and get better reception out of your wireless mics from here. Okay. Now, if you're not dealing with a whole lot of noise floor or anything like that, and you are in an environment where you're not sure where your wireless mics are going to end up, then a more omnidirectional antenna might be advantageous for you. Because then it doesn't matter where in the room your mic goes, this will pick up in all directions. So really, choose the right equipment for the right scenario. Now, I'm going to describe something that I think all of us are guilty of at least once in our lives, some of us many times, that I have been in trouble for personally from the Shure Corporation, which is, we all make mistakes. I just was what I like to call verbally slapped on the hand by Shure once upon a time, because I was having some RF issues, getting some equipment to work properly. So I described what I was doing, and he said, "You're doing what?" And what I was doing was saying, well, I've got this really cool LPDA fin from Shure. It was the one that had the amplifier in the side. And I was like, man, I'm really having some issues, so I kind of boosted it up. He goes, "You're doing what?" I said, "Well, I'm using the antenna like everybody else does." He goes, "Okay, how big is your stage?" And I said, "Well, typical rock and roll, 40 to 60 foot wide." He goes, "Do yourself a favor, get rid of the LPDA, put the dipole whip on it, and be done with it. And you're going to have a lot better of a time." And I was like, "What?" And sure enough, I went down to, got rid of this guy, put this guy on it, and it resolved almost all my problems. Yeah. These? Nah. You're gonna have to get these from the manufacturer. Yeah. So, just have someone provide it for you. Yeah. And the reason that he told me to do that is because in RF, unlike, once again, I'm going to date myself. Does anybody remember Home Improvement? Tim the Toolman Taylor? Yeah. More power? Yeah. Anyway, he was always about more power, right? In RF, more power can be really detrimental to what you're doing. The rule of thumb is only use the amount of power that you absolutely need to get the job done. So what I was doing is I was feeding way too much energy with my LPDA, getting the energy in, boosting it into the receiver, and it was actually causing a lot of issues with noise floor and some other intermodulation issues that we'll talk about here in a second. So that being said, these aren't always the answer to your RF issues or bigger antennas or more power. Yeah?
Another way to say that is it's like overdriving an audio, but on mixer.
Yeah. So you're going to overdrive. So I'm repeating for yeah, you're going to overdrive. It's like overdriving, distorting the signal, and we'll take a look at that a little more closely here in a second. One of my favorite stories is with a longtime friend of mine that used to work for a company that's very close to here. Oh yeah, well, at the time of the story, he didn't work here. So my friend Trevor, and we went through this whole thing with Shure and trainings with wireless mics and everything. And I walked into one of his shows, and he had these LPDAs set up, and it wasn't even that far of a throw. And I looked up, and they were cranked to +10 on the amplifier, and I was like, Trevor, we've been through this. And he goes, yeah, I know. But he did it anyway because that's what people expected to see, a lot of times. So, but just hold your ground sometimes, just know that boosting everything and boosting the power in RF can actually be detrimental to the end goal. So, yeah.
Never mind. I was going to tell a story, but it won't translate well in the mic. It's fine. It's fine.
Okay. No,
All this RF, you don't have to.
yeah, with all this RF, I chose to use a single microphone. All right. Now, the next video I'm going to play, I think, is really super cool. It's kind of longer, but it's going to go with what we want to transition to antenna orientation and why it's so important.
Here I have a 300 megahertz oscillator and a 100 watt radio frequency amplifier that's going to be amplifying the output of our 300 megahertz oscillator.
100 watts is a lot if you don't know.
This dipole antenna to transmit radio waves. Let's turn it on and see what effect it has on this 8 watt, 1 foot fluorescent light bulb. If I bring the fluorescent light bulb near the end of the transmitting antenna, it lights up, even though it nor I is plugged into anything. If I slide it along the length of the dipole antenna, we notice that the intensity decreases and is a minimum at the middle of the dipole antenna, and then increases in intensity again as I go towards the outer edge of the other side. It's then dim once again, once I go toward the middle, and maximum on the ends. So this is evidence that there's standing waves that are set up on our dipole antenna with a maximum in potential or antinodes at the ends and a minimum in potential or a node in the middle. We can see a similar effect if I take a simple receiving piece of copper pipe as a receiving antenna. It's about 48 centimeters long. And if I hold it in the middle and bring the fluorescent bulb toward the end, it lights up even though it is not plugged into anything. And as I move the fluorescent bulb along the length, the amplitude is dimmest at the middle and maximum at the ends. as we saw for the transmitting antenna. Recognizing that the current is the maximum in the middle of our antenna, we're going to switch to one that has a single light bulb and use its brightness as a measure of intensity. As I move the receiving antenna closer to the transmitting antenna, the amplitude gets progressively stronger. We can also see that if I rotate the antenna relative to the orientation of the transmitting antenna, its intensity is 0 when the receiving antenna is perpendicular to the transmitting antenna, and maximum when it is parallel. We can also see that if I rotate the antenna or align the antenna along the axis of the receiving antenna, that the strength goes down. And if I rotate it so that it is perpendicular to the axis of the antenna, its intensity is 0. Lastly, if we look at the intensity of the antenna or the receiving antenna as I move in a cylinder around the transmitting antenna at a constant distance, we can see that the intensity stays constant. These help us visualize the radiation pattern off of the transmitting antenna. Here we have a different kind of antenna from the one that we saw earlier. Formerly, that long, straight conducting antenna was a dipole antenna that was sensitive to the electric field. This is a B-field antenna that is sensitive to the magnetic field. It has a loop to have currents induced within it, and a light bulb that is connected across a portion of the loop, and also 2 parallel plates that act as a tiny capacitor, which we can tune using this ruler to adjust the spacing between them. Let's take a look at the luminosity of our detector in several different orientations. We can see that with the loop parallel to the plane of the antenna, it has a high brightness, whereas if I rotate it by 90 degrees this way, it has a minimum brightness, and if I rotate it by 90 degrees once again, it also has a smaller brightness as compared to the original orientation. This tells us that the B field is maximum in this direction, that it is parallel to the normal of the plane of of the B field loop antenna.
All right. So what did we learn? Placement is key. Orientation is key. What's that? Wear a lead vest. Yeah. Seriously, I saw this and I was like, no wonder I feel funny all the time. Yeah.
I noted he was wearing one of the Rode wireless mics right there, and it wasn't interfering at all.
Yeah. Hayden?
My question is, what type of antenna is a wireless handheld mic? Because
That's a great question.
I don't know if it matters based on how the performance holding it.
I'm going to refer to my to a guy that teaches a lot of really good classes that you should all attend. Guy by the name of Pat Brown, and the answer is it depends. So he asked what kind of antenna is in a wireless mic. So it's going to depend on manufacturer and the design. A lot of them now are actually helical, so like a small helical in the bottom. Some of them are just straight antennas, depending on what the manufacturer wants to do. So what they feel is best for their product. So another thing to extrapolate from this whole video was this does not necessarily need an orientation. On your transmit antenna, it's not going to care because it's going to pick up equally all the way around. So, but if you're dealing with one of these, then orientation of antenna is actually extremely important. So, like especially with like body packs, if your antenna is straight up and down, then you're going to want your antenna straight up and down. So, and just I've had a lot of kids in the past say, well, does it always need to come up the top? No, you can switch your body pack around. The orientation, just vertical, horizontal needs to be the same. So that's pretty key. In fact, we can even demonstrate that a little bit more. We're going to look at the spectrum analyzer here. And I'm just going to fire this microphone up. You guys are going to see it pop up right there. Okay. So what we've got is right now on the spectrum analyzer, this is in the same orientation as the analyzer antenna over here. And we've got some pretty good signal. Okay. So what I'm going to do now is we're just going to bend this like that. And you'll see I've lost a little bit. And if I can come off to the side, just like we saw in the video, it's going to fluctuate a little bit. But if I go, because these are actually emanating more of that donut pattern, if I come in and go tip to tip, if I can get it just right, you're going to start losing a little bit. It worked really well earlier. There it goes. Okay. So you lose quite a bit because there's actually no energy really radiating out of the tip of this thing. So, and there's not going to pick up a whole lot off the tip to tip. So be aware of that. So even just by changing its orientation, we're going to get a fluctuation in power. Yes?
What we're seeing right now and what we saw in the video
Uh-huh.
is what we're seeing in real time, the animation that we saw earlier with the waves.
Yes.
But we're seeing that now in real time.
Well, it's going to be a combination of waves and actually just how it's radiating. And it's got to be in the same field. Yep. Yep. Uh-huh.
Like some of our speakers will be like women, and sometimes we have it upside down where the antenna's pointed down. Most of the presenters will have the antenna pointed up. In a case like that, like how detriment is it where your antenna is being pointed or how it's being distributed? Like what I need to, how would you set that up so that you're sure that that's not going to cause any interference or?
Okay. So the question was, how important is it for this to be up, down, orientation, like out on your presenters, because some presenters like it certain ways, to hide it or whatever. So basically, to set that up for best case scenario is your receive antenna. Let's just pick this guy for fun. If it's straight up, receive antenna is like this. If it's like this, it can stay like this. Yes, absolutely. If you have a presenter that prefers to do the side, you're going to want to go to the side.
I've never seen that, but okay.
Yeah. Or if you've got something that's going to be just all over the place, you might want to go in a 45 degree because then you're kind of in between the two. The helical does not matter. You're right. So it's all going to depend on your antenna and what's going on here. Yeah.
Classic example is a guitar strap.
Yeah, I was just going to say guitar straps. Guitar straps a lot of times are going to be at 45s. So if you're having issues with your guitar player or something like that, you might want to take, even if it's on the back side of your receiver, like a single receiver, and your guitar strap is like this, you can even just take it like that. And you're going to get yeah, so you want your orientation to be like this. Not so much. Right. The same orientation is going to give you the maximum amount. Yeah, maximum amount of transfer there. So, Like I said, a lot of wireless mics now, the little stubby at the end is helical, so it's going around as well. So it's not going to matter antenna orientation with those either. Okay? Yeah, no problem. Yeah.
How would that orientation change for the fin? Would it be
For the fin? So the fin is basically just a whole bunch of dipoles. So you're going to want it if, once again, you know, if your pack is going to be like this, take your fin, you know, like that. But now we're talking about one transmitter, one fin. If you've got 20 of these things and they're anywhere from here to here, now what are you going to do? You're going to get a helical, or you're just going to be like, well, the average says that it's going to be somewhere like there. No, you know. So really, it comes down to pay attention to what your receiver strength is, what's going on, and make adjustments accordingly.
One other comment is, this goes back to like you can break a lot of little rules. Notice how hard he tried to get it to fail so spectacularly. You can make a lot of adjustments and still be okay.
Yeah. So for the people listening, he said it goes back to the beginning where you can make a lot of little mistakes, and I actually had to try to get it to fail as much as I did. And by the way, I even had to try even harder because I put this pack down to transmitting at 1 milliwatt to make it do that, okay, which is its lowest setting. And I don't actually really know anybody that runs their packs at 1 milliwatt except for stories I've heard out of Japan. So, yeah.
Since the helical is so beneficial, what advantages does the fin have that the helical doesn't?
The helical's big.
No, that's it.
Yeah.
That's it. Fin small, helical big.
Yeah.
Okay. So.
Or asking about the advantage of why didn't we just always do helical?
Yeah.
Because the helical also has forward gain, it might actually get too close to your transmitters and distort the signal. So once again, but you might get away with it. If that's the only mistake you're making, you just might get away with that. Might.
While we're talking about helicals,
Uh-huh.
while I've been on tour, a lot of the bands that like we open up for will have the helical.
Uh-huh.
And they freak out about cellular devices being on board. What's
Yeah.
the reasoning behind that? Like, no one's really explaining to me. They just scream at me, turn off your phone. Okay.
Okay, so I'm not going to, asking about cellular devices and helical antennas, I'm not going to say I'm the foremost authority on this. This is going to be RF theories by Aaron. One, if there's a bunch of cell phones going off and on, it raises the noise floor maybe a little bit, or it sends some energy where it shouldn't go. But even in airplanes, it's a metal tube, so you're focusing all that energy. But my theory is that you just want to turn people to turn their phones off so they're actually more focused on what's going on. Yeah. So I don't know. That sometimes I think that guys that get that antsy about it have had a bad experience, couldn't explain why they had a bad experience, so they just want to shut everything down instead of finding out what the real problem was.
I was just curious.
Yeah.
No one's really explained why was it so detrimental for me to cut my cellular frequency off.
Especially when now all your cellular devices are in a completely different band than TV and 20 years ago? Yeah, things weren't quite as good as isolating 20 years ago, so that could have been more of a legitimate issue. But devices are getting better. Yeah. Yeah, no problem. So then going back to some of the graphics earlier, remember that where you have the antenna in the room really matters. And we're going to show some, I'm going to show some pictures that I went to Sennheiser's making wireless work, which I highly suggest, even though this class might be informative in some ways. If you ever get the chance to go to Sennheiser, you need to do it. Those guys are phenomenal. But let's talk about antenna placement in real-world scenarios. And this is what really drives me nuts, and really a driving force behind Pole Sound University is we see a lot of things that are done by quote-unquote professionals out in the real world, and then you see this and you start to question how professional our whole industry is. So right here we have some antennas in a rack and an install. Those are the receivers. inside of a steel enclosure. Yeah, the antennas. Remember how we said metal and RF don't get along? Yeah, it's wonderful. There they are in the back. Okay? Now, it gets even worse because the antenna orientation is like this out of the back of the receiver. Okay? And the only way RF can get into this particular rack is this way. And we just talked about how there's no energy picked up from the tip, right? So, I don't know, maybe they got away with it. Maybe they didn't, I don't know. I'm just saying, this is the kind of stuff that once you have this knowledge and you start seeing the stuff in the world, you just start to shake your head. Here's another one. I love this one. This one's kind of hard to see. So we're just going to think about the chain link fence, right, and all the openings. Well, when you start putting all your microphone cables and all your cables that are metal, right, and you start interweaving them, we're just creating essentially a chain link fence with openings for RF, right? So just to give you an idea, because I know you can't see them all, I went through and highlighted most of the antennas, not all. Okay? Just the ones that are, yeah. Yeah. And these aren't on the outside of the cables, these are intertwined with the cables. So tell me they're not having RF issues in this rack. Yeah, it's amazing. There's some other little quarter waves in there. Remember how I said the quarter waves weren't the most efficient? There's some quarter waves wrapped around in there somewhere too. So it's awesome. Don't do this, or don't do these things. This next one is actually, at first you're like, oh, this is innovative. Like they were worried about orientation. Yeah, but being a gym, you also don't want the basketballs to hit your fins. But yeah, we're just going to chalk this up to a fail. So, and the funny thing is there is actually a high school up in the area north of here, and I walked in and I saw almost this exact picture. Their fins were behind because they wanted their tech booth to be safe and not get broken into. So it was behind like this metal fence thing, and their antennas were inside the cage. So, and they were like, yeah, we have a lot of mic dropouts. I was like, you think? I'm like, does anything work? So yeah, there you go. Okay, here's some other things. You need a ground plane, but your antenna also, you don't want your antenna parallel to your ground plane, perpendicular. And then, look, I know we are all guilty of this one. If anybody says they're not guilty, you're a liar. That you have a whole bunch of single receivers at like a corporate event, and you've got some table space, so you put them out on the table, and you stack receivers on top of each other, and you just start to kind of fan out your antennas, right? Anybody not done this? If you haven't done it, you haven't worked here long enough. Okay? Once again, you can get away with one mistake on a few of them. This is also a very classic high school scenario that I run into all the time, because they'll rent extra mics from a company for their plays, and then they'll just stack them on top of each other. But then recently if you're not subscribed to PA of the Day on any of the social medias, you probably should be, because this one was quite popular recently. It's phenomenal. Once again, chain link fence and antenna, even receive antennas, when you get them that close, they start interacting with each other and desensitizing one another, and you're just asking for problems. Like, once again, this worked for you? I really wish we could find the person that operated this and ask them how their show went, because I'm dying to know. Yeah. Yeah. Maybe. Yep. Okay. I just love this one. All right. Now, the other thing that we really want to try to do is try to maximize placement of antennas to transmitters. The idea is to try to get your transmitter as close to your antenna as possible without distorting it and trying to keep obstructions out of the way, everything like that. And sometimes you just need to go to extreme measures. This was taken from a guy by the name of James Stoffo, who's a genius in the world. And they went through rehearsals for the Super Bowl, and everything was fine. And then all of a sudden, they didn't anticipate the people on the sidelines during the national anthem. And he was in charge of RF, and he freaked out. And so the person holding the helical antenna is his daughter. And he said, take this, push your way. I don't care who you have to shove out of the way. You get in front of everybody, and you point that thing right at her. And it probably saved the national anthem of this particular game. So, and once again, he got the antenna as close to his transmitter as possible. Yeah. Yeah, we're going to talk about that in a sec. Don't jump ahead on me, Austin. Jeez. We're getting there. All right. So real quick, we're just going to talk about some transmitter types. I think most of us have seen all these. We don't need to spend a whole lot of time doing this. Yeah. All right. So now, thanks, Austin. Here's the other thing that we have to, because we want to keep, your antenna close to your transmitter, but there's the flip side that you're going to get power loss through cable. So now we have to start calculating what's the most beneficial thing. So what we want to do is you've got all your different cable types over here, and then we've got some real-world scenarios. Here's it blown up just a little bit better. So your original scenario is, once again, 500 feet from your transmitter to your receiver, which I don't know why they chose 500 feet, because that's a long ways. Probably a lot more, but it works for demonstration purposes. So you think, all right, so Aaron told me, get the antenna closer. So I've got so much cable, I can half that by 250 feet. So I gained 6 dB of strength because of the inverse square law by halving the distance. So I'm good. I gained 6 dB. But the downside is I had to run so much cable that I took 9.5 dB of loss over the cable to the receiver. So actually, I've done more harm than good by trying to do that scenario. So then we do the more appropriate calculation where I run a short cable, but I gained 4.5 dB because I used an LPDA, and that's its forward gain. So I actually gained 4.5 dB of signal strength coming in, which is better than what I started off with. So really, it comes down to, calculating out what you're doing, what the benefits are, and knowing what you're going to do. Now, the other thing is, once again, we talked earlier about getting too close. So, Aladdin.
Please come closer. Too close, a little too close. There.
Okay. I like this clip to demonstrate that. Because when you get too close, it distorts his face. The same thing's going to happen when you get your two antennas too close. You can actually overload your receiver, distort the signal, and you're going to cause some intermodulation distortion. So, once again, with antennas, there's good things to do, there's bad things to do. When it comes to distribution, and this is all going to be manufacturer dependent, so it's really important that you guys really go through your manuals, find out what the manufacturer suggests and what you can get away with. So once again, you remember our fan-out situation with all of our antennas? The goal is let's get it down to 2 antennas only for all of our microphone receivers. The antennas don't care. You can load antennas up with tons and tons of frequencies. They don't care. What does care is everything that happens after the antenna. So if I've got 2 receivers, I can get it down to 2 antennas. I use a passive splitter. The splitters are going to lose you signal strength, typically somewhere in the realm of 3 dB. Yeah.
I happen to have my chart, because I was just looking at it. 3 dB for the split plus -2 for insertion loss, so 5 dB.
5 dB total? Okay. So once again, do your research, find out what this is going to do. Losing 5 dB for this scenario, depending on distance of, transmitter to receiver, losing 5 dB through this setup actually may not be too bad. You could probably get away with it. So, and then there's active distribution. So you get a distribution unit. You get your 2 antennas to go into your distribution. It has amplified signals out so that you get to each unit correctly. Once again, for example, Shure ULXDs, they've designed them so that you can actually daisy chain 3 of their units together safely. As soon as you want to do more than 3 daisy chain, then you have to get a distribution unit, and then you can do a set of 3, a set of 3, a set of 3, a set of 3, and potentially get, what is that, 48 channels of ULXD off one distribution setup and do it correctly. Because each time you daisy chain out of a receiver into a receiver, you are going to lose something. So if the manufacturer has not compensated for that, then you're losing more and more. Shure has done a little bit of compensation, and they say you can get away with 3.
That's just what I was about to ask. Typically on a wireless receiver that has a cascade out, is that like amplified or is that just passive?
It kind of depends on manufacturer. If Shure says you can get away with 3, there's probably going to be a touch of amplification on it, or at least something to compensate just a little bit. But if it's passive, you're not losing enough for it to be super detrimental. Yeah. The numbers on the passive distribution. It was for the splitter, it was 3 dB, and then for insertion loss is another 2 down. Yeah.
So one of the favorite things I learned from that Sennheiser class is as you daisy chain, you can daisy chain a lot, especially like if you've got multiple distros, as long as you're amplifying. But what happens is at the edges of the frequency band, you get distortion, ripples, so it gets messy at the edges. So if you have mics that you need to put, at the bottom of your distribution, the frequencies on those mics should be in the middle of your frequency band.
Okay. So if you couldn't hear, when you daisy chain, the outer limits of your distribution get a little distorted or a little weird. So the more you do distribution, try to get your frequencies into the middle of your band as much as possible so they're not on the outlying edges of what you're trying to do. Which is something I hadn't heard, so thanks.
Who's in the class? You were there.
We were in the same class? I don't think we were in the same class. That's okay. I say different things in every class too. So, all right. So now we're going to go to the other side. We've talked about antenna placement, receive. Now we're going to talk a little bit about transmitter optimization, signal to noise ratios, stuff like that. In analog, you wanted the hottest amount of audio coming into that transmitter pack. Because in analog, the hotter your audio is, you actually get extra transmit distance out of it because it sends a stronger signal for the FM modulation, which makes the signal stronger, which means it's going to go slightly farther. So the guys at Shure, actually in the class that I attended, apparently Chris and I were in different classes, or who knows. Legally, they cannot make a transmitter that can distort. So even though you see the button or the light on the transmitter in an analog pack distort, that's your warning. But they cannot transmit distorted audio. So keep that in mind. Don't be too scared of trying to get it too terribly. Now, you can distort your element. You can distort everything, but other things, but you're not going to actually distort the analog pack, RF. Okay? So once again, you've got your transmitter gain stage. If you don't get your audio up, then you're going to be sitting closer to that noise floor down there, which means you could actually get some signal dropout the closer you get to your noise floor. But if you can get your audio gain up and like that, you're going to get farther distance and you're going to stay out of that noise floor. I love this picture because it have you guys noticed that yet? No matter how hard we work to get all of our stuff optimized, as soon as you hand your transmitter to the talent, there's no telling what's going to happen. So, yeah. Once again, transmitter placement. Handheld microphones, it's almost free air, you know, but I think we've all seen it when the person gets a little handsy with their handheld transmitter and they just want to hold it down by the antenna and they grab around the antenna with their hand. And if you don't know this yet, you will know it very soon that people, I like to say people are dense and RF does not go through the body very well. So you grab around the antenna and all of a sudden you've got dropouts. The transmitters, don't keep it off skin. So for people that do theater or a lot of corporate work or something like this or like that, it's really common to just put this on the inside of someone's clothing and this ends up touching their skin. And that's going to really eat up a lot of the RF. Not to mention, RF does not like to travel through salt water. So your sweat contains salt. So you combine this with skin, sweat, and all of a sudden you've got dropouts. There are certain things I've seen people do. Put some heat shrink over this just to keep it off the skin to try to help out. I've even seen people get desperate and they went to a restaurant real quick and got some straws and put the straw over it. I mean,
I've done that with success.
With success, there you go. Chris is living, breathing proof. Yeah, even if you can get like this in between two pieces of clothing, you know, it'll just help out. I think we've all seen the people take the transmitter and just stuff it in a pocket. And so let's see what happens when we do that. We're gonna go look at our spectrum analyzer again. So once again, we're transmitting and all I have to do is take this and just bend the antenna. You're gonna see it start to drop. And if it gets stuffed in a pocket, it's going to start getting really low. And I talked about people wrapping hands around it. Well, let's even increase our distance just a little bit. This is doing a little bit too well for my liking. Once again, you can get away with a mistake or two. Or if you put it just behind me, there you go. How much your body. So this guy actually means keeping it straight and in orientation and everything is pretty crucial.
Is there a reason why you just dropped out?
I don't know.
That's what I'm asking. Did that cause that?
No.
Okay.
I don't know. I know a guy. All right.
So on the body packs and stuff, why do they, because I've seen the, wrap cardboard around and put a straw on it, so on and so forth. Why don't they more heavily insulate those antennas right up the hand?
That's a good question.
Everybody's always putting straws on the back.
Maybe just durability of materials or something. I don't know. I don't know. Cost? I don't. It's a good question. I've never heard a good reason for that. All right. Oh, something that we should mention as well. Antenna length is important for the bandwidth. If you get too short of an antenna for what you're trying to do, actually the wavelengths will can basically bounce back back down the wire. So too short of an antenna could cause some issues for you as well. Keep that in the back of your mind. So make sure that you've got the appropriate antenna length. All right, there's some other stuff that can happen or that's going on. Some people like to use tone key squelch. This happens. Squelch is just basically, it's for all intents and purposes, it's a gate. So your wireless mic receiver, if it doesn't see enough signal, it might auto mute. Sennheiser for many years, I hated Sennheiser for this. You had squelch settings, but inevitably it wasn't good enough, and you constantly just get out of Shure, out of Sennheiser stuff. Shure's auto squelching system has been great for many years. Some people use what's called a tone key squelch to get their microphones to open up. So if you ever see this on an analyzer, just be aware that that's what's going on. Setting your squelch level, you've got your RF noise down here. So you want to make sure that your squelch level is high enough to get above your noise floor, anything that's happening down there. But you want to make sure it's low enough that it doesn't cause a dropout in audio. All right. So we talked about LED walls. What we have here is your classic LED wall. It's turned off. Here's the noise floor environment right there. All we're going to do is we're just going to turn it on. Okay, I mentioned that LED walls put out a lot of RF. There's proof of it. Then we're going to put an image on it. Life is getting worse. Noise floor goes up. All these spikes are going up. And then the worst thing that can happen on an LED wall to create a lot of problems with you is white. So when it gets really bright, this is what LED walls are doing to your environment. Tell me how you're supposed to get wireless mics to work in that. Okay? And this is where antenna placement comes into play in a big, big way to make sure that you're getting above all of this. All right, transmitted power. We talked roughly about this. Once again, a lot of times I think we just, to solve problems, it's like up the power, up the power. Well, it's all about the ohms, logarithmic power, and all this physics that goes into it. So increasing 25 milliwatts to 50 milliwatts is only a 3 dB increase. So that's double the power. You're going to go through your batteries a lot faster. And once again, I mentioned this earlier, the rule of thumb is only use enough RF power to get the job done. Now here's the big one that we're going to spend the rest of our time on is intermodulation distortion. This is the math behind it, and then I'm going to show you guys why this is important. Because analog-wise, this is a big deal. When you get two analog transmitters in the same environment, once again, these are just some numbers to make the math easy. So transmitter 1 is at 189, transmitter 2 is at 191. You do the math, and they actually will create these spikes out here that it's called intermodulation distortion. When this happens, this is what can interfere with other microphones. So you do this, and you're going to create interference for others. And we can actually watch this happen live. So what we're going to do is we're going to turn on this guy. This is an analog transmitter. And you're going to see him pop up over here in a second. There he is. This is our other analog transmitter. And I'm going to kind of keep these separated a little bit. So there's my two transmitters, right? All I have to do is get these guys to interact a little bit. And you can see all of that interference pop up right there. Okay? So now what happens if I park another wireless mic right here? Am I going to have issues? You betcha. So now think about doing this 40 or 50 times over, because it's not like, oh, let's do the math between these two and I get these, and then I add a third one and it's only going to interact between like maybe one of these other ones. The third transmitter, you're going to get this same scenario with this one plus this one. And then if I add in fourth, it's going to interact with all the rest. So all of a sudden your intermod issues are going up exponentially. So this is what happens with analog. Now, the way digital works, the digital transmission kind of puts this into basically it acts as a linear device, and we can actually see. We're going to turn the high-powered one off, because once again, I use that one to make scenarios look a lot worse than they are, but it's for a good reason. So now I've got these two. Okay. Even though one's analog, one's digital, look, I could get these close. And because this one's digital, it's not going to create the intermods like the two analog ones are going to do. So there's a lot of, and that's why digital is also so popular right now, is that because you can park a lot of digital transmitters in the same amount of space without, with way less concern of intermodulation distortion than with analog. Now be aware that you've got to know what you're dealing with, because in your monitors, analog still, okay? Because the latency is still too long. A lot of transmitters are, so many transmitters are going digital now, but there's still a lot of analog products out there. So the question is, I'm going to get my guy to, hey, thanks. So just so you guys know, when we're talking about fifth order, third order, seventh order intermodulation distortion, so if these are your first two primary frequencies, the first spikes out here are the third order intermodulation. The second orders are actually way out here. So it's the third, the fifth, and the seventh that we're most concerned about typically. But if these fall within the usable bandwidth that you're in, you're going to want to be aware of these guys too. The best way to deal with these, there's just another, here's a couple ways to deal with intermodulation distortion. If you've got a lot of transmitters that you just, on a show, and they're not all going to be out together, or you've got to pack them closer together, get yourself some bread tins and isolate all the transmitters in these bread tins to keep all the RF contained, so you're not creating all this intermod when it's not really necessary. I've used this same thing on a lot of theater shows. It helps out a lot. So, what do we got to do to deal with it? We got to frequency coordinate. This is huge. There's a lot of different things to help coordinate this. There's IAS, which is very, very popular. It's really good. It's kind of, the user interface is actually kind of clunky at times, but I would say this is the most trusted frequency coordinator software out there. It's really good. You can band plan in it, stuff like that. The next one is obviously probably the most common that people really like, Shure's Wireless Workbench. One of the problems with Wireless Workbench is out of the box, it's kind of locked. It's almost too conservative if you're doing a high frequency count. It has a problem spitting out a lot of frequencies if you're going for that. So there are ways to loosen it up. We could probably teach a whole nother class on just how to use it and get it to open up so that you can find all the channels that you need. It does take a while. There's lots of different things. Invisible waves could do it. The one nice thing about Wireless Workbench is if you're on all Shure products, it does your coordination. You hit deploy if they're networked, and it just programs everything for you, and it's really nice. It's really cool. IAS definitely does not do that. So once you get your coordination, you have to go in and type everything and sync everything up. IAS, just a kind of a screenshot, looks like this, so that you can go and do all your groups. What I mean by sometimes you can band plan is you can actually get like transmitting frequencies kind of grouped together and receive frequencies grouped together pretty darn easy. It's really hard to do that through wireless workbench. It takes a lot of work. That's what it looks like. Now, wireless workbench, by the way, also, it's really useful if you want to get a quick scan of your environment. You can use almost any one of the receivers networked, get a scan of what's going on. Chris's recommendation is when you're setting up wireless workbench, do not fully trust the zip code or database. It's inaccurate. So it'll get you probably 90% of the way there, but you want to do another scan to make sure that the data you're getting is actually current to your environment. All right. Just to kind of show you, this is from wireless workbench and the spacing between intermods and stuff. It kind of, if you were to actually study these a little bit more, you would see how locked down workbench is, and you could actually compare to see how open you can make IAS. So one of the things to know that the manufacturers do, let's say you've got a few wireless mics, you don't have wireless workbench with you, or it's just not, for whatever reason, you can't really do a coordination and you are in a pretty isolated building, you're not worried about outside interference a whole lot. When you look at the groups and channels of your mics, if you can do your microphones in the same group, for example, I've got 4 receivers. I can do group 1, channel 1, group 1, channel 2, group 1, channel 3, group 1, channel 4. That is a coordinated list from the manufacturer. So to compensate for intermodulation distortion. Now, you cannot do group 1, channel 1, group 2, channel 1. That's no longer coordinated. You have to keep them within the same group. I think this is completely accurate. So, yeah, all the math gets complicated really fast. We're going to kind of just speed through the last little part. This is kind of just general knowledge stuff. Licensed versus unlicensed, what you can get away with, what it means to be licensed. It's not worth it for you to be licensed as necessarily as an individual. It's better to be licensed as like a company or like a school district. But it also lets the FCC know how many wireless mics are being used out there, what the situation really is. And it's just kind of a good idea to get licensed if you can as a big group. So what makes you eligible for a license? So you being licensed as an individual probably doesn't really get you anywhere. Analysis tools. This is scanning tools. There's a lot of different ones. If you were going to become the RF guy for the company or want to get to that point, at some point I would really highly suggest you at least start out with a little RF Explorer just so you can see the environment. You can export scans out of this guy, and he's relatively cheap. Everything else is quite a bit more expensive, as you can see. And if you are a computer hack like our friend Austin, then RTL SDRs are really convenient and do really well at just plugging into your laptop and doing scans. And you can do a lot more with them, but we're not going to discuss that here because we're not going to get people in trouble. Right, Austin? Right. As as he's already recorded my microphone earlier. All right. So here are some resources here that are really good. And there's a lot of learning to be done and refresher stuff to be done online that you guys can go check out. And for anybody that knows my brother and he thought he was really funny and didn't think I'd check my slides, but I did, so now I just do this on purpose. Yeah. Yeah. Yep, it's fantastic. Anyway, yes, Manny. Yeah. How far? Just one? Yeah, we don't need to see it. Oh, the websites? Yeah. Oh, shoot. I probably went one too far again. Hopefully it stays on this one. Yeah. Yeah. Chris and I, honestly, him and I have probably coordinated on this class over the years many times together, so.
What's funny is it says where I stole most of the stuff for this presentation, Chris and I included. That actual slide he straight up stole from mine and just put Chris and I included.
Cool, huh? Yeah. The whole slide I stole from him and just added that. Yeah. So it's wonderful. Sorry. I know a lot of people want to go into like software and stuff like that. Like I said, that's almost an entire class on its own. The purpose of this one was just kind of give you guys like what's going on with RF. Try to make you a little more successful with what you can do quickly on show site. Get you through the show with the least amount of problems. And remember, if you're having dropouts, you've probably got a few mistakes going on, just not one.
How many sticks do you have right now?
How many mistakes do I have right now? I have at least 2. At least 2. So, yeah. There you go. I'll admit it. One of them is my antenna is right in between my arm and my body. So I'm fully aware of that. Yeah. So once again, sometimes if you know that it's your mistake, own it. Go with it. So I'm willing to sit here and take questions. We're going to probably let the online people go. You guys can go. Thanks for coming. I hope you guys look forward to many more classes. The next one is going to be soon with Deward, who honestly, you'll learn so much from the guy talking about amplifiers. To me, amplifiers for a long time were like this mystical just thing that just did one little simple thing. They're so much more complicated than that. And once you understand them, you'll love it. So I'll be sending out information and RSVPs for that one again soon. If you guys have any questions, please feel free to talk to me afterwards. For anybody online, everybody is more than welcome to email me at any time. I really like to just help people out and be successful at their shows. And that's why this is kind of open up to the community. So with that, thanks.